Let's go through this exam. Okay, question 1. In this particular question, if you have D-allose memorized, then you got it in the bank. But if you don't, then we just have to analyze the question. And we see that it's saying D. So that means on these carbons right here, the last stereocenter, in all those sugars, we need the alcohol on the right side. And that's the only one with the alcohol on the right side. So that's the only D sugar possible. All the others are L sugars. So that's the only answer possible. Question 2, what is the major product of the reaction? Let's see here. So in this particular one, what are we doing here? We are looking at a Claisen condensation. We have an ester. We have our base. And you see that that base matches that piece. That's very, very important. That allows the reaction to abstract this alpha proton right here. And then when that abstracts that proton, you're going to get this intermediate right here. Okay, and then you will use that to do a attack on another ester. So we could use it. You'll see that I'm drawing the exact same ester like this, but what you're going to have happen is this guy's going to come in and attack. So we have a Claisen condensation reaction. And when you follow through with that whole mechanism, you will see that answer choice D is the correct answer. Question 3. IUPAC. The correct answer for this problem would be B. Question 4. What are the resonance structures of the enolate formed? Let's see. So when we look at that, we know that the alpha protons are the ones that are acidic. So that's alpha and that's alpha. But this alpha right there has no protons. The only one that has alpha protons is this guy right here. There's 2 of them. And so when that generic base comes in, whatever it may be, it's going to come in and grab that proton and make a resonance structure. And the resonance structure that the enolate that I just made looks like this. Like that. And then from that you could draw a resonance structure where one of those lone pairs come down and then those electrons go there. So we would have something that looks like this. And so when we're trying to find that, we will see that this guy right here matches that guy. And then we see that this guy matches that guy. So the answer then for that would have to be C. So with question 5, what's the predicted major product? Well, here are these reagents here where you have excess of the methyl iodide and silver oxide. You know that, and you have an amine. That's a Hoffman elimination. And so with those conditions, we can eliminate those 3 right off the bat. And then we just have to remember that, hey, we're going to have an elimination product. Are we going to have the Zaitsev product or the Hoffman product? Well, the Hoffman product is where you put the alkene at the, you're going to abstract the hydrogen at the least steric site. So we have these hydrogens right here that can be abstracted. And so if you take off, let's circle this one blue. If you take that proton off, then you're going to generate the more substituted alkene. But if you abstract the more accessible hydrogen due to sterics, you're going to see that you're going to get this product right here, which is called the Hoffman product, or the least substituted alkene. So B is the correct answer. Okay, number 6 is a intramolecular Claisen reaction here. Okay, so what we first notice is that our base is O-ethoxide, which matches the esters. That's very important, because now that allows that ethoxide species to come and abstract a proton. We can abstract this one. And when it comes and abstracts that, we're going to generate ourselves an enolate looking species. We could also represent it like this. 1, 2, 3, 4, 5. Like this. So that's going to be negatively charged. And then that's going to come in and attack. If we number these carbons 1, 2, 3, 4, 5, that lone pair is going to come in and attack carbon 5 to form a 5-membered ring. Okay. If you draw your 5-membered ring there, and if we call this carbon 1, okay, we see that it formed a bond with carbon 5. So there's our 5-membered ring, so that makes that 2, 3, and 4. What's attached to carbon 1 still? We have a carbonyl, okay, and then we have the ester part. So that piece right here is this piece. Now, attached to carbon 5, what do we have? Attached to carbon 5, we're going to have the O minus, and then attached the ethoxide piece. This piece is that piece. And it's not an ethoxide, but ethoxy piece. Now what's going to happen now? That's going to collapse down. So the lone pairs here. Going to collapse down, kick that guy off. That's going to generate this species right here. Okay, double bonded O like that. Okay. So that's after step 1. Then when we add some water or some aqueous acid, what does that do to esters? It chops off the esters. And so that's going to generate carboxylic acids. So there's our carboxylic acid after step 2. Now what do we have here? We have beta keto acid. So there's alpha. Beta keto acids. When you add a little bit of acid and heat, what do? They decarboxylate. And so that means CO2 is lost. And that gets lost as CO2 right there. So that's going to fall off and generate, after you do the decarboxylation reaction, you're going to generate your ketone right there. So that would have to be answer A. So right here is a Gilman reaction. We have the Gilman reagent right there, and that's going to attack, let's see here, nope, not like that. That Gilman does a Michael reaction here in which the Gilman is going to add the methyl to the beta position. So there's alpha, there's beta, and what is it going to add? One of the methyls. And so we would predict the product to look like this. So there's our 1, 2, 3, 4 carbons. 1, 2, 3, 4. And what did we do? We added a methyl to carbon 3. Overall, that's what happens. And so you see that that would have to be answer B. Question 8. Which of the following compounds can be identified through the haloform reaction? That one, you have to find a methyl ketone. That's what the haloform reactions work with, are methyl ketones. And that right there is a methyl ketone. So answer choice C. So we are trying to find non-reducing sugars. So what we're going to do is try to find the hemiacetals. And there's a hemiacetal right there. So that's reducible. We can see another hemiacetal right there. That's reducible. In this product right here, or sucrose, what we see is we find the anomeric carbons, okay? And we see that those are both acetals. So that's a non-reducing sugar. Come here to maltose, we see there's a hemiacetal, so that's a reducing sugar. And then when we come to this last sugar, we see that there's our anomeric carbon, that's an acetal. And if we find our other acetal or anomeric carbon, it would be this guy, and that is also an acetal, not a hemiacetal. So that would make that guy a non-reducing sugar as well. So that gives us only 2. Which one of the indicated hydrogens is the most acidic? Well, this hydrogen right there is sandwiched in between a ketone and an ester, and it's also alpha to another ketone. That just has a lot of functional groups there that can help stabilize a negative charge when that hydrogen is abstracted, making that the most acidic. Question 11. What's the major predicted product for the following reaction scheme? Okay. So we're going to what? First do, we're going to abstract that proton. To make this species. Then we'll treat that with the methyl bromide. So we'll put the methyl there. And then adding acid is going to hydrolyze the esters into carboxylic acids. And when you have a diacid right there, in this position where they have the 2 acids at position 1, 2, and 3, in that 1-3 relationship, that's going to decarboxylate one of the groups. Okay, so let's just say this one. That's going to fall off as CO2, leaving only this. When it decarboxylates, it's going to leave that. So that's your final product, and that matches answer choice D. Okay, for question 12, we have a nitro group, and we want to convert that into a amine or an aniline form. So the only reagents that will get that job done would be answer choice A. Which of the following molecules is the most basic? Answer choice B. And all the other examples there, the lone pairs on these nitrogens, okay, they're attached to like this A, that can resonate in. So those lone pairs right there, they're caught up in resonance, so they're not solely used to act as a base. Whereas this nitrogen species, that lone pair is localized. It's just on the nitrogen, whereas this guy over here, that lone pair over there, is delocalized. And so that makes that guy, or answer choice B, the most basic, because those lone pairs are localized just on that nitrogen. Okay, question 14 is a reductive amination reaction. And in that reductive amination, that first step right there, we're going to generate this species right there. But then that species, that amine, the amine is going to get reduced by the sodium cyanoborohydride to give us the amine. So the amine, or answer choice D, is the correct answer. What reactants would give the aldol condensation product? In this one, we have to go back to that we just are going to sever that bond. And so we're going to have those two pieces. We're going to have the ring, and then we're going to have a carbon. So that carbon right there is that carbon right there. And so that's just going to be our aldehyde piece. So if we circle this piece right there is that piece. And then the other half would have to look like that. Okay? So this piece right there is that piece. And so the only answer choices that match that analysis would be E. Okay, so for the free response questions here, so we want a alpha Pyranose. So the Pyranose is telling us that we're going to have a 6-membered ring. Like so. And then that's going to be carbon 1. Carbon 1, 2, 3, 4, 5. 1, 2, all the way to carbon 5, which is going to be CH2OH right there. So that's carbon 5. So at carbon 1, when we compare carbon 1 and carbon 5, when they are on opposite sides, when the OH is on opposite sides of one another, like this, that's alpha. And then what we focus on is right here. All those groups are on the right side. So that means that they have to be down in the Haworth projection. So carbon 2, the OH is on the right side, so that means it has to be down. In the carbon 3, the OH is up because it's on the left side. And if we number these 3 and 4, carbon 4, the OH is on the right side, so that has to be down like that. So the way we gave the points for this question is just 1 point for the substituents all in the correct order or orientation. So that's plus 5 possible points. And then if you go to this, to the beta Pyranose, okay, so everything has to match up here. So if we look at carbons 2 through 4, they have to match what we just did. So that means carbon 2 is down, carbon 3 is up, and carbon 4 is down. And then it's telling us, we can see that this sugar is a D sugar. So that means this group right here, CH2OH, has to be in that orientation. And then the beta is telling us that the alcohol in carbon 1 has to be on the same side as that group. So we can see +1 for another 5 points. So that's how you would get those 10 total points for that question. Okay, so for this problem right here, the answer needs to be this guy. Just like that. That is a Robinson annulation reaction. So that's the full, so that's a plus 8 points right there. And then it says right here to circle the Michael acceptor. And that's the Michael acceptor, so that's our plus 2 for a total of 10 points. Now, we broke this down right here. I gave you 2 points for 2 6-membered rings. Two 6-membered rings. Okay, I gave you 2 points if you have a alpha beta unsaturated compound anywhere in the molecule. If you have 2 6-membered rings, 2 points. If you have alpha beta saturated carbonyl compound somewhere, 2 points. You got 2 points if you have 2 ketones. And then you got 2 points right there if it was exactly correct. Okay. So that's how we broke down the points for that one right there. So this one right here, so we're looking for the kinetic enolate, so which means that LDA, which is a really good base that I'm just going to represent like that, we will grab that hydrogen, the least sterically hindered hydrogen. And so that's going to give us this enolate right here. And then that enolate is going to react with the ethyl bromide. So the lone pair is going to have to come down. Pi is going to come here in an SN2 fashion. To do a alkylation event at the alpha carbon just like that. So that is the product that you would expect, and you get 5 points for that structure, and then you would get 5 points for the mechanism. Question 19. This is just remembering your reactions here. So when you have a secondary amine and you treat it with nitrous acid, that's going to generate a nitrosamine. that looks like this. So that's a nitrosamine, that would be +3. When you have aniline with nitrous acid, it forms the diazonium salt. And so that would look like this. And our chloride's floating around there. And to be more precise, that would be the aryl diazonium salt because it's attached, the diazonium's attached to the aryl group or the benzene ring. So that would be +3 points there. Now, this reaction right here is a Gabriel amine synthesis, which is good at making our primary amines. So that's going to generate this as our major product, like that. And that would be another +3. And the name of that molecule, which is the bonus question here, would be a amphetamine. So we have amphetamines. Kind of crazy what governments do to soldiers and to people. Tested interesting or different drugs on people. Okay, so that is, and so that for that you got an extra 1 point if you answered that correctly, and then you got 1 point for trying. Okay, so question 19 is out of 10 points with a possibility of getting a 1 point bonus. And let's see, and that's it. Okay.